Tonight, we're going to look at the strangest kind of lost it is possible to be. Lost with every instrument working perfectly. Picture a ship that has suffered nothing. No collision, no fire, no failure. The hull is sound. The reactor is warm and steady. The air is clean, the water is cycling, the lights come up on schedule because a clock somewhere still believes in mornings. Every gauge on every panel reports a number inside its safe band. By any standard, a shipyard would recognize this vessel is in perfect health. And not one system aboard it can tell you which way home is. That is not a malfunction. That is the ordinary condition of deep space, and it arrives in stages, each one quietly removing something that was doing more work than anyone noticed. First the ground goes, and with it the whole idea of a direction called down. Then the horizon goes, and with it every sense of scale you have ever used. Then the landmarks go, because at these distances there are no landmarks, only points of light that refuse to resolve into anything. Then the conversation goes, not because the radio breaks, but because the answer takes longer to arrive than the question was good for. And at the end of that sequence, standing in a bright warm room surrounded by functioning machinery, you would be somewhere. You would simply have no way to say where, and no way to say it to anyone who could do something about it. The distance is not the cruelty here. The cruelty is the silence of the instruments. A compass fails on Earth, and you notice, because a broken compass still points somewhere, and the somewhere is wrong. Out there, the instruments do not lie to you. They tell you the truth, and the truth is that they have nothing to measure against. Which raises the question this episode is built on. Is there anything in the universe steady enough and loud enough and long-lived enough to serve as a landmark for a traveler with no landmarks at all? By the end of tonight, you're going to understand exactly how each of our navigation methods fails and at what distance it stops working, what the one genuine solution is, and how close we have actually come to proving it, and why solving the problem of knowing where you are does almost nothing to solve the problem of getting back. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first thing to be honest about is that a position is not a thing. It is a relationship. When you say you are in a particular city, you are not describing a property of yourself. You are describing where you sit relative to a coastline, a river, a set of roads, and a grid that someone drew on a map and everyone else agreed to use. Strip away the coastline and the river and the roads and the agreement, and the statement evaporates. It was never about you. It was about the arrangement. This sounds like a philosophical point. It is actually the entire engineering problem, and it explains why deep space navigation is hard in a way that ordinary navigation is not. Every navigational instrument humans have ever built is a device for comparing yourself to something else. A compass compares you to a planetary magnetic field. A sextant compares you to the angle between a star and a horizon. A speedometer compares your wheels to a road. A satellite receiver compares the arrival times of signals from objects whose orbits are published in advance. Not one of them measures your position. All of them measure a difference, and then arithmetic does the rest. So the question of whether you can find your way home in deep space is really a question about inventory. It comes down to what is left out there to compare yourself to. What has stayed put? What is bright enough to detect? What is distinctive enough to identify? And what is stable enough that its behavior tonight tells you something reliable about where you are tonight? The honest answer is that the inventory is very short, shorter than almost anyone expects, and the items on it fail in different ways at different distances, which is why the failure is not a single wall you hit, but a staircase you descend, losing one sense at a time. There is one more thing worth saying up front. The problem is not that space is empty. Space is not empty. It is full of stars and gas and dust and radiation and the accumulated light of 100 billion galaxies pouring in from every direction at once. The problem is the opposite. Space is full of things that are almost identical to each other, at distances you cannot measure, moving in ways you cannot see, along a line of sight that flattens all of it onto a single sheet. A sky full of stars is not a map. It is a photograph of a map, taken from an unknown angle at an unknown time with the depth removed. Everything that follows is an attempt to put the depth back. Navigation on Earth is easy, and it is worth understanding exactly why, because every reason is something space takes away. Start with the ground. The surface of a planet is a two-dimensional sheet, and a sheet is an extraordinarily forgiving thing to be lost on. It cuts the problem from 3 unknowns to 2 immediately. You cannot be 1,000 meters above the road or 1,000 meters below it. You are on the road or you are not, and the set of places you might be shrinks by a whole dimension before you have measured anything at all. Then there is the fact that the sheet holds still. Continents do move, but at speeds measured in centimeters per year, which is to say they hold still on every time scale a traveler cares about. A landmark you saw yesterday is where you left it. This is such a deep assumption that it is almost impossible to notice you are making it. Every map humans have ever drawn quietly depends on the subjects of the map not wandering off. Then there is the horizon, which is doing more work than any single instrument. A horizon gives you a reference plane. It gives you a level. It gives you a way to measure the angle of a star above the ground, which is the whole basis of celestial navigation as it was practiced for centuries. A sailor with a sextant, an accurate clock, and a table of star positions can find a position anywhere on the ocean, and every part of that method rests on there being a visible edge where the sea meets the sky. Then there is scale. On a planet, you know how big things are. A mountain has a size you have some intuition for. A tree has a size. A building has a size. And because you know how big they are, you know how far away they are. Apparent size and known size together give you distance, instantly and without conscious effort. This is such a fundamental part of seeing that most people never learn it is a calculation. And then finally, there is the network. Modern navigation on Earth is not really navigation at all. It is a subscription service. A constellation of satellites broadcasts precisely timed signals. A receiver compares their arrival times, and the arithmetic delivers a position anywhere on the planet in seconds. The entire skill has been replaced by infrastructure. Every one of those 5 gifts, a reduced dimension, a stationary reference, a level plane, a known scale, and a broadcast network is a local feature of living on a planet inside a satellite constellation. None of them is a property of the universe. Take a ship away from the planet, and they do not degrade gracefully. They come off one at a time, cleanly, like keys removed from a ring. The first subtraction is the most disorienting and the least discussed because it is not about instruments at all. It is about the fact that looking out a window stops telling you anything. In deep space, there is no down. Gravity is still present. Gravity is always present. It never switches off. But at a great distance from any large mass, its pull is too weak and too uniform to create the sensation of a direction. A ship coasting between stars is in free fall with respect to everything around it, and free fall feels exactly like nothing. So the first thing that goes is orientation, not the ability to orient. A ship can define its own axes and hold them with gyroscopes, but the sense that one particular orientation is correct. The second thing that goes is the horizon, and with it, the reference plane. There is no edge anywhere. Look out in any direction and you get the same thing, a black field with points of light in it. Turn the ship 180 degrees and you get a different arrangement of points of light, equally featureless, equally uninformative about which way you should be facing. The third and strangest loss is scale. Every point of light in that field is a point. It has no measurable size. A star 10 light years away and a star 10,000 light years away both render as a dot, and the dots are not distinguishable by shape because neither has a shape. Brightness does not save you because brightness confounds two things at once: how much light the star actually produces and how far away it is. A dim nearby star and a brilliant distant one can arrive at your eye as identical dots. Without knowing one of those two quantities independently, you cannot recover the other. So the view from the window is a flat picture. Everything in it is projected onto a single sphere with you at the center at a radius of unknown. That sphere is what astronomers call the celestial sphere, and for most of human history, people took it seriously as a real object, a dome with lights fixed to it. That was a mistake, but it was a very understandable mistake, because from a single vantage point, that is precisely what the sky is. Here is the part that matters for a traveler. If the sky is a projection with the depth removed, then two very different positions in space can produce very similar skies. Move a few light years and the pattern shifts, but it shifts subtly and mostly among the nearest stars. Move in a direction along which the nearest stars happen to be sparse and the sky barely changes at all. You could travel an enormous distance and look out of the window and see a sky that a careless observer would call the same sky. The window is not a navigation instrument. It never was. On a planet, it borrowed its authority from the ground, and out there the ground is gone. If you cannot look outside for a position, the obvious alternative is to stop looking outside and start counting. This is dead reckoning, and it is the oldest navigation method there is. You know where you started. You measure everything that happens to you afterward, every acceleration in every direction for the whole voyage, and you add it all up. Acceleration integrated once gives velocity. Velocity integrated once gives position. In principle, a ship that carefully records its own accelerations from the moment it leaves never needs to look at anything external at all. It carries its position with it in a running total. In principle. The difficulty is that this method has a specific and unforgiving mathematical weakness, and understanding it explains why every serious spacecraft still wants an external fix eventually. An accelerometer does not measure acceleration perfectly. It has a bias, a small constant offset, a tiny amount of acceleration it reports even when there is none. Bias is not noise. Noise averages out over time. Bias does not. It accumulates, and because the calculation integrates twice, it accumulates twice. Follow the arithmetic. A constant bias, integrated once, produces a velocity error that grows in a straight line with time. That velocity error, integrated again, produces a position error that grows with the square of time. Double the length of the voyage, and you do not double the error. You quadruple it. Put a number on it. Suppose your accelerometer has a bias of 1 part in a million of Earth's surface gravity. A very good instrument, far better than anything in a phone. That is about 9.8 millionths of a meter per second squared. Run it for 1 year and the accumulated position error is roughly 4,900 kilometers. 4,900 kilometers is not much on a stellar scale. It is, however, more than a third of the diameter of the Earth, from an instrument that was wrong by 1 part in a million over a single year, with nothing going wrong. Run the same instrument for a century, and the error is not 100 times larger. It is 10,000 times larger. Around 49 million kilometers, about a third of the distance from here to the sun. And that is the optimistic version, because the bias is not really constant. It drifts with temperature, with age, with the slow accumulation of radiation damage in the instrument itself. Every one of those drifts gets integrated twice as well. So dead reckoning is not a solution. It is a way of postponing the problem. It works beautifully over short intervals, which is why it is used constantly, and it degrades relentlessly over long ones, which is why it is never used alone. Every dead reckoning system in existence is designed around the assumption that it will be corrected by an external measurement before its error becomes intolerable. The question for a ship in deep space is what external measurement it is waiting for. The most familiar answer is the one that is least available, and it is worth being precise about why. Satellite navigation works by a beautifully simple trick. A set of satellites in known orbits each broadcast a signal stamped with the exact time it left. A receiver picks up several of those signals at once and compares their arrival times. Because each signal travels at the speed of light, the difference in arrival times is a difference in distance, and with enough satellites, the receiver can solve for the one position consistent with all of them. It is not magic. It is the same triangulation a surveyor does, executed at light speed by a chip that costs less than a sandwich. But every part of that depends on being inside the constellation. The satellites broadcast downward, toward the planet they serve, because that is where their customers are. Their antennas are shaped for that. Their signal strength is budgeted for that. NASA's own description of the limitation is blunt. Satellite navigation is not an option for far-flung missions because the signal weakens quickly as you travel beyond the satellite network around Earth. Leave that shell and the signals do not gently fade into a less accurate service. They stop being usable. And even if you could somehow keep receiving them from an enormous distance, the geometry would destroy you before the signal strength did. Triangulation depends on the reference points being spread widely across your sky. From far enough away, the entire constellation collapses into a single small patch in one direction. All the satellites give you nearly the same measurement, and nearly the same measurement several times is not several measurements. It is one with extra steps. And here is the thing nobody likes to say plainly about modern navigation. Almost none of us know how to do it. We know how to consult a device that does it. The skill has been fully absorbed into infrastructure, so completely that the failure mode most people can imagine is a dead battery, not an absent civilization. A ship in deep space is not experiencing a technical problem with its receiver. It is experiencing the total absence of the society that built the reference points. That absence is the real subject of this episode. Everything we call navigation on Earth is a form of borrowing from a planet, from a network, from a set of published tables that somebody maintains. The traveler in deep space cannot borrow. Whatever they use has to be something the universe supplies on its own, without maintenance, without cooperation, and without anyone knowing they need it. There is exactly one category of object that qualifies. We will get there, but first we have to watch the last familiar method fail, and it fails in the most human way of all. For every spacecraft humans have actually sent into deep space, the answer to the navigation problem has been the same. Ask home. The Deep Space Network is the system that answers. It is a set of very large radio antennas placed roughly a third of the way around the planet from each other, so that as the Earth turns, at least one of them is always facing any given direction in the sky. A spacecraft transmits, an antenna receives, and from that exchange, the navigators extract a startling amount of information. The first thing they get is range. Send a signal up, have the spacecraft return it, and measure the round trip. Multiply by the speed of light, divide by 2, and you have the distance with remarkable precision, down to meters at distances measured in billions of kilometers. That is not an exaggeration of the technique's power. Time is the one quantity humans measure better than anything else, and range is a time measurement wearing a disguise. The second thing they get is speed along the line of sight. The returned signal comes back slightly shifted in frequency because the spacecraft was moving while it transmitted. That is the Doppler effect, the same physics that changes the pitch of a passing siren, applied to a radio carrier and measured to a precision that would let you detect a walking pace at the edge of the solar system. So range and speed come almost free. What does not come free is direction, and direction is most of the problem. Range tells you that the spacecraft lies somewhere on a sphere of a certain radius centered on Earth. Doppler tells you how fast that radius is changing. Neither tells you where on the sphere. To pin down the two angular coordinates, to say not just how far, but which way, you need something else entirely. And for the first 2 decades of planetary exploration, this was the weakest link in the whole enterprise. Doppler tracking determines a spacecraft declination, its angle above or below the celestial equator, poorly. Navigators knew exactly how far away their probe was and were considerably less certain about where to point. That is a strange kind of blindness to sit with. You can know the distance to a machine to within a few meters across 1 billion kilometers and still not know precisely which direction to look. Distance is a scalar. It falls out of a clock. Direction is a vector, and vectors are expensive. The solution the Deep Space Network eventually built for this is one of the most elegant pieces of measurement engineering ever assembled, and it is also, for our purposes tonight, the exact point at which the whole approach begins to break down. Because it is spectacularly precise as an angle, and an angle is not a position. An angle is a position only when you also know the distance, and the further away the traveler goes, the more brutally that multiplication punishes them. The technique is called delta differential one-way ranging, and the idea behind it is worth understanding because it is genuinely clever. Two antennas, far apart on Earth, listen to the same spacecraft at the same time. Because they are in different places, the signal arrives at one very slightly before the other. That difference in arrival time depends on the angle of the spacecraft relative to the line between the two antennas. Measure the difference precisely enough and you have measured the angle. The trouble is that everything in between corrupts the measurement. The signal passes through the solar wind, through the interplanetary medium, through Earth's ionosphere and atmosphere, and each of those adds a delay that is not known in advance. So the technique adds a second step, and the second step is the beautiful part. Immediately after observing the spacecraft, both antennas swing to look at a distant quasar sitting nearly in the same direction, an object so far away that it is, for these purposes, infinitely distant and perfectly fixed. They make the same measurement on the quasar. Then they subtract. Because the two observations pass through nearly the same atmosphere, nearly the same solar wind, nearly the same everything. The subtraction cancels the errors and leaves the pure geometry. That is where the delta in the name comes from. It is a differential measurement against a fixed point in the sky. The result is a plane of sky angle good to roughly 1 nanoradian. That number deserves a moment. A nanoradian is a billionth of a radian. It is the angle subtended by a coin about 2 centimeters across, viewed from 20,000 kilometers away. In routine operations, the delivered accuracy is more like 2 to 5 nanoradians with about 98% reliability. But the system's design point, the thing it was built to achieve, is 1. This is the most precise angular measurement humans routinely make on a moving target, and it is a genuine achievement of a kind that rarely gets celebrated. Now watch what happens when you carry it outward. An angular error becomes a position error when you multiply it by distance. At Voyager 1's current distance of roughly 170 astronomical units, 1 nanoradian corresponds to about 25 kilometers of uncertainty across the line of sight. That is extraordinary. It is a machine the size of a small bus, located to within the length of a commute, across 25 billion kilometers of vacuum. Carry it to the nearest star. Proxima Centauri is 4.24 light years away, which is about 40 trillion kilometers. The same 1 nanoradian measurement now leaves you uncertain by about 40,000 kilometers, more than 3 Earth diameters. Carry it further. At 55.8 light years, That same superb measurement is uncertain by roughly 528,000 kilometers, which is farther than the distance from here to the moon and back again with room to spare. The instrument did not get worse. The instrument is identical. Distance simply multiplies everything, including your best work. There is a second problem with navigating by conversation, and it has nothing to do with precision. It has to do with the fact that a conversation takes time, and that time is not negotiable. Voyager 1 is the working example because it is the most distant object our species has ever put anywhere. In mid-2026, it sits roughly 170 astronomical units from the Sun. A signal from Earth takes about 23 hours to reach it. On the 18th of November this year, that number becomes exactly 24 hours, and Voyager 1 becomes the first thing humans have built to stand one full light day away from the planet that made it. Consider what that means for navigation. If a navigator on Earth wants to know where Voyager is and what it should do about it, the sequence is: send a request, wait 23 hours, the spacecraft receives it and replies, wait another 23 hours, the reply arrives. 46 hours from question to answer, rising to 48 after November. 2 days. Every navigational decision made about Voyager 1 is therefore made using a picture of the spacecraft situation that is at minimum a day old, and any instruction sent back arrives a day after it was composed, into a situation that has moved on. The navigators are not steering a spacecraft, they are steering a memory of one. This is manageable for Voyager because Voyager is coasting. Nothing is happening quickly. It has no engine burns left to plan, no encounters ahead, nothing that requires a decision inside a 2-day window. The latency is an inconvenience, not a threat. Now imagine the same arrangement around a star. Proxima Centauri is 4.24 light years away. A question sent there and answered comes back in 8.5 years. Send a request for a navigational fix when you are 25, and the answer arrives when you are 33, describing where you were when you asked. At that point, the word conversation stops applying. You are not talking to home. You are receiving letters from a version of home that existed years ago, containing advice about a version of you that no longer exists. The information is not wrong. It is simply about a different moment, and there is no way to make it be about this one. And the lifetime tax is symmetrical, which is the part that stings. It is not only that you cannot get an answer quickly, it is that nobody at home can know what happened to you until the same interval has passed. If something goes wrong at 4 light years, the news of it takes over 4 years to arrive, and any response takes over 4 years to come back. The rescue is not late. The rescue is a category that does not exist at that distance, and we will come back to why. So even in the best case, a working transmitter, a listening antenna, a civilization still interested, navigation by conversation degrades from a live service into a correspondence, and then from a correspondence into an archive. The signal keeps working. The usefulness does not. So set the radio aside. Assume nobody is answering. What can a traveler see? Here's the number that ought to sit at the center of this whole subject, and it is smaller than almost anyone guesses. Our Sun has an absolute magnitude of about 4.83. Absolute magnitude is a way of comparing stars fairly. It is how bright a star would appear if you placed it at a standard distance of 10 parsecs, roughly 32.5 light years. On that scale, the Sun is unremarkable, a middling yellow star, brighter than most of its neighbors only because most stars are small red ones, and dimmer by far than anything a person would describe as impressive. The human eye, under a genuinely dark sky, in good conditions, can detect stars down to about magnitude 6. That is the naked eye limit, and it has been the boundary of human astronomy for most of our history. Put those two numbers together with the distance modulus formula, and you get a distance. The Sun reaches apparent magnitude 6 at about 17.1 parsecs. In light years, that is 55.8. 55.8 light years. That is the range of home. Travel farther than that in any direction, and the Sun is not merely hard to find in the sky. It is not in the sky. It has dropped below the threshold of human vision entirely, and no amount of staring, no amount of dark adaptation, no amount of knowing exactly where to look will bring it back. A person standing on the deck of a ship 56 light years out, looking directly at the correct patch of blackness, sees nothing at all. 55.8 light years is a very short distance by the standards of this subject. The nearest star is 4.24 light years away, so the Sun stays visible for only about 13 times that gap. There are somewhere around 2,000 stars within that radius, a modest neighborhood, a few blocks of a city that contains hundreds of billions. And the loss is not gradual in the way you might hope. Magnitude is a logarithmic scale, and the last stretch is cruel. At half that distance, the Sun is a comfortable magnitude 4.5, easy to pick out. At 40 light years, it is around magnitude 5.5, a faint thing you would need a dark night to catch. At 55, it flickers at the edge of perception, and then it is gone, and it stays gone forever. For every distance beyond. There is no ceremony to it, no last glimpse, no fading over the course of a voyage that anyone aboard would notice happening. Just a threshold crossed somewhere in the middle of an ordinary week, after which the star that made every atom in your body is no longer among the things a human being can see. If the Sun is invisible past 55.8 light years, the obvious next move is to navigate by the other stars instead. There are billions of them. Surely a pattern that rich contains enough information to locate yourself. It does, in principle. In practice, it betrays you 3 separate ways, and each betrayal is worth understanding on its own. The first is that stars are not labeled. This sounds trivial, and it is not. Recognizing a star means matching what you see against a catalog, and matching requires distinguishing features. Stars have very few. They have a brightness, which, as we have established, confounds distance with luminosity. They have a color, which tells you the surface temperature, and therefore roughly what kind of star it is. But there are billions of stars in each category, and from a strange vantage point, with the familiar patterns broken, A yellow star of middling brightness is a description that fits an enormous number of candidates. The second betrayal is that the patterns themselves are local. Constellations are not structures. They are lines of sight. The stars of a constellation are usually nowhere near each other in space. They merely happen to fall in similar directions when viewed from here. Move a meaningful distance and the arrangement shears apart, near stars sliding across the background of far ones. The recognizable sky is a feature of a particular vantage point, not a feature of the galaxy, and a traveler who has moved far enough to need a map has moved far enough to lose the one they memorized. The third betrayal is the one that closes the trap. Suppose you do identify a star with certainty, a distinctive one, a bright supergiant, something unmistakable. All you have learned is a direction. You have learned that this object lies that way. You have not learned how far along that line you are, and you have no way to learn it from the sighting alone, because the star's apparent brightness depends on your distance from it, and you do not know your distance from it. The measurement is circular. To break the circle, you need at least 3 identified objects, and a way to turn each sighting into a distance rather than a direction. Directions alone will fix your orientation beautifully. A ship can determine exactly which way it is pointing from a star sighting, and spacecraft do this constantly with star trackers. Small cameras that photograph a patch of sky, match the pattern against an onboard catalog, and report the attitude to within arcseconds. Attitude is not position. A star tracker tells a spacecraft which way it is facing with superb precision and tells it absolutely nothing about where it is. It is a compass, not a map, and the distinction is the whole difficulty. There is exactly one method that turns a direction into a distance without assuming anything about the object being measured, and it is the oldest trick in surveying. Hold up a finger at arm's length. Close one eye, then the other. The finger jumps against the background. It jumps because your 2 eyes are in slightly different places, and the amount of the jump depends on how far away the finger is. Bring it closer and the jump gets bigger. Push it further and the jump shrinks. Measure the jump, know the distance between your eyes, and trigonometry gives you the range. That is parallax, and it is the only direct measurement of stellar distance we have. Everything else in the astronomical distance ladder, the brightness of variable stars, the properties of certain supernovae, the redshift of galaxies, is calibrated against parallax at the bottom. Parallax is where the ladder touches the ground. For an observer on Earth, the 2 eyes are the same telescope 6 months apart. The Earth moves from one side of its orbit to the other in that time, giving a baseline of 2 astronomical units, about 300 million kilometers. Photograph a nearby star in January and again in July. Measure how far it appears to have shifted against the more distant background, and the arithmetic delivers a distance. The shifts are minuscule. The parallax angle for the nearest star to the Sun is under 1 arcsecond, under 1/3600th of a degree. That is why nobody measured a stellar parallax until 1838, despite people having looked for it since antiquity. The absence of a detectable parallax was, for 2,000 years, one of the strongest arguments against the Earth moving at all. The parallax was there. It was simply far too small to see with the instruments available, which is a useful reminder that a null result and a small result can look identical for a very long time. Here is what makes parallax the honest measurement. It assumes nothing about the star. It does not care how bright the star truly is, what type it is, how old it is, or what it is made of. It is pure geometry, a baseline, an angle, a distance. Any error in it comes from your measurement of the angle, not from a model that might be wrong. And here is its unforgiving limitation. The size of the shift is inversely proportional to the distance. Double the distance and you halve the angle. A star 10 times farther gives a shift 10 times smaller. Eventually, the shift drops below the precision of your instrument, and at that point, the method does not become approximate. It returns nothing. Everything, therefore, depends on how finely you can measure an angle and on how wide a baseline you can arrange. Humans have pushed the first of those about as far as engineering currently allows. The second has not moved in the entire history of the technique. The best answer humanity has produced to the parallax problem is a spacecraft called Gaia, and it is worth being precise about what it achieved, because the number is both magnificent and sobering. Gaia spent years spinning slowly in space, sweeping its two telescopes across the whole sky again and again, measuring the positions of stars over and over as the Earth carried it around the sun. Its third data release contains more than 1.8 billion sources, 1.8 billion individual objects, each with a measured position, a brightness, a color, and for a great many of them, a motion and a distance. That is the largest and most precise three-dimensional map of anything that has ever been made. It is one of the genuinely great scientific achievements of this century, and it rewrote large parts of what we know about the structure and history of our galaxy. It is also about 1% of the stars in the Milky Way. The galaxy contains somewhere between 100 and 400 billion stars. The range is that wide because most stars are small, dim red dwarfs that are difficult to count even nearby and impossible to count at a distance. Against 100 billion, 1.8 billion is under 2%. Against 400 billion, it is under 0.5%. Call it about 1%, and you will not be far wrong, and the imprecision of that estimate is itself part of the story. And here's the thing worth saying plainly. The best map of our galaxy that our civilization has ever produced is missing 99% of its subject, and there is no plan, no proposal, and no plausible technology on any drawing board anywhere that would fix that. It is not a funding problem. It is a physics problem. Even within the mapped 1%, the quality is uneven in a way that matters enormously for navigation. Gaia's angular precision is roughly 24 to 25 microarcseconds for a reasonably bright star, an angle so small it is comparable to measuring the width of a human hair from 1,000 kilometers away. From that precision, you get distances accurate to 1% or better for about 11 million stars, all of them within roughly 800 parsecs, which is around 2,600 light years. Push out to a few kiloparsecs, and the accuracy falls to about 10%, and around 150 million stars sit in that tier. Push to 5 kiloparsecs, and the errors approach 50%, at which point a distance is no longer a measurement, but an opinion. The Milky Way's disk is roughly 15 kiloparsecs in radius. The overwhelming majority of it has never had a direct distance measured to anything inside it, and on current physics, it never will. It is worth sitting with why parallax stops, because the reason is structural rather than technological, and structural limits are the ones that do not yield to effort. The baseline is 2 astronomical units. That is not an engineering choice. It is the diameter of Earth's orbit, and it is the widest baseline that a stationary observer can obtain by waiting, because waiting only gets you as far as the Earth goes. You could imagine widening it. Put a telescope in an orbit as far out as Jupiter, and the baseline grows to about 10 astronomical units, 5 times better, which converts to 5 times the distance range at the same angular precision. Push to Neptune's orbit, and you gain a factor of 30. These are real proposals. Missions of exactly this shape have been sketched. They are also, notice, factors of 5 and 30 applied to a distance range of a couple of thousand light years in a galaxy 100,000 light years across. A factor of 30 takes the reliable range from a small neighborhood to a slightly larger neighborhood. It does not take it to the far side. There is a subtler problem with waiting for a wider baseline, and it is the one that ends the discussion for a traveler. Parallax requires observing the same star from 2 positions and comparing. If the 2 positions are separated by decades of travel, then the star has moved during those decades, and so has everything you were measuring it against. You are no longer comparing 2 views of a fixed arrangement. You are comparing 2 views of an arrangement that changed by an amount you do not know in a direction you cannot determine, and the change is mixed inseparably into the signal you were trying to read. For nearby stars over a few years, this is a solvable nuisance. Astronomers untangle parallax from proper motion routinely, because the parallax repeats annually and the proper motion accumulates steadily, and 2 different time signatures can be separated. Over a voyage, that separation collapses. The traveler's own motion, the star's motion, and the parallax all become the same kind of drift. So the honest summary of the geometric method is this. Parallax gives true distances, with no assumptions, out to a range that is large compared with a human neighborhood and negligible compared with a galaxy. Beyond that range, every distance we quote for anything comes from a chain of inference, from assuming that a certain kind of star has a certain true brightness, that a certain kind of explosion releases a certain energy, that the expansion of the universe has behaved in a certain way. Those chains are well built, and they are checked constantly, and they are still chains. They are not the ground. A traveler who has gone beyond parallax range has left the part of the universe that has been measured and entered the part that has been modeled. There is one more thing standing between a traveler and a working map, and it is the most physical obstacle of all. It is dust. The space between stars is not perfectly clear. It contains gas, mostly hydrogen, and it contains grains of solid material, carbon, silicates, ices, each one perhaps a fraction of a micron across. The density is absurdly low by any laboratory standard. A cubic centimeter of interstellar space might contain a single dust grain in a volume the size of a large room. If you had a sample of it in front of you, you would call it a hard vacuum without hesitation. But a line of sight through the galaxy is thousands of light years long, and over that path length, even an absurdly thin haze accumulates. The grains absorb and scatter starlight, preferentially at shorter wavelengths, which is why distant stars in the plane of the Milky Way look redder than they should. The blue light was removed along the way. In the most obstructed direction we know, the effect is total. Look toward the center of our own galaxy, the direction of Sagittarius, the brightest and most crowded region of the sky, and you are looking through roughly 30 magnitudes of visual extinction. 30 magnitudes. The magnitude scale is logarithmic, with 5 magnitudes representing a factor of 100 in brightness. 30 magnitudes is a factor of a trillion. 1 part in a million of the visible light leaving the galactic center in our direction actually reaches us. That is why nobody in the whole history of human civilization ever saw the center of the Milky Way. Every culture that mapped the sky, every astronomer who cataloged it, every navigator who steered by it, none of them saw the object our entire galaxy revolves around. It was behind a wall the whole time. We only know it is there because radio waves and infrared light pass through dust in a way visible light does not, and because we built instruments that can see in those bands all of it within the last century. For a traveler, the consequence is direct. The single most useful landmark imaginable, the massive, unmistakable, unmoving center of the galaxy you are lost inside, is invisible in the band your eyes work in, and the obscuration is not uniform. It varies enormously from one direction to another, so a survey of the sky is not a survey of the galaxy. It is a survey of the parts of the galaxy that happen to have clear sight lines. Even Gaia, mapping in optical light, sees its completeness fall away toward the galactic plane, dropping on the most reddened sight lines to around 70% of the sources that should be there. The map has holes in it, and the holes are exactly where the interesting structure is. Take stock, because this is the point where the practical situation becomes clear. A traveler in deep space carries, at best, the finest star catalog our civilization has produced. It has 1.8 billion entries. It has excellent distances for a few million stars nearby, usable distances for 150 million more, and directions without reliable distances for the rest. It has holes wherever dust intervenes. It is a magnificent document, and it is, functionally, a chart of one small district in a very large city, with several streets missing and the downtown blacked out. To use a chart, you must find yourself on it. That is a specific operation. Identify several charted objects, measure their directions and distances from where you are, and find the single point in the chart from which those measurements would all be correct. It is triangulation with extra steps, and it works. It works, that is, while the objects you can identify have known distances in the catalog. Once you are far enough out that the recognizable stars are all in the poorly measured tier, the intersection stops being a point and starts being a volume. A fuzzy region, hundreds of light years across, inside which any of a great many positions would produce the sky you are looking at. And there is a final indignity, which brings us back to the anchor. The chart is centered on the sun because we made it and everything in it is quoted relative to us. But past 55.8 light years, the sun is not one of the objects you can see. You are holding a map whose origin point is invisible from where you stand. You could, in principle, locate yourself relative to a handful of bright charted stars and then compute where the sun must therefore be. The direction would come out of the arithmetic, it would be a number on a screen pointing at a patch of dark that contains nothing your eye can detect. That is a peculiar situation to be in, and it has no equivalent in any human experience of being lost. A person lost in a forest cannot see their house, but they know that houses exist, that the forest ends, and that walking in a straight line will eventually produce a road. A sailor without instruments can still see that the sea has an edge where it meets the sky. In deep space, past 55.8 light years, home is not hidden behind something. It is below the threshold of detection, in a direction indistinguishable from every other direction, and it will stay that way for the rest of the voyage no matter which way you go. Everything up to this point has been a description of what has been taken away. The remainder of tonight is about the one thing that is still there, and then about the much harder question of what having it actually buys you. Underneath every problem described so far, there is a deeper one, and it is not an engineering limitation. It is a property of the universe, established over a century ago, and it cannot be worked around by building anything better. There is no absolute rest. Ask how fast the ship is moving, and the question has no answer until you specify what you're measuring against. Relative to the sun, the Earth moves at about 30 kilometers per second. Relative to the center of the galaxy, the sun moves at about 230 kilometers per second, carrying the Earth along. Relative to the diffuse glow left over from the early universe, the whole local group of galaxies moves at something over 600 kilometers per second. Every one of those numbers is correct. None of them is more correct than the others. There is no experiment you can run inside a sealed, unaccelerated ship that will tell you your true speed, because there is no such quantity. This is not a gap in our knowledge. It is a result. Relativity does not say we have failed to find the absolute frame. It says the laws of physics come out identical in every unaccelerated frame, which means the concept has no observable content. A universe with a hidden absolute frame and a universe without one would look exactly the same from the inside, which is physics' way of saying the question was malformed. For a navigator, this has a strange consequence, and it is worth stating plainly because it is easy to skate past. Every coordinate system anyone has ever used in space is a convention that somebody chose. The one that dominates astronomy centers on the sun system and orients itself using a set of distant radio sources. It is enormously useful. It is also an agreement, not a discovery, and its usefulness is entirely a function of everyone having the same copy of it. A ship far from home is still inside that coordinate system, in the sense that mathematics has no edges. It is outside it in every sense that matters, because the reference objects that define it are either invisible or unresolvable from where the ship sits. And so we arrive at the honest form of the question that has been sitting under this whole episode. If there is no absolute frame, no fixed ground, and no still point, what does it even mean to know where you are? The answer is that it means finding objects on which everyone can agree, not because those objects are truly motionless, since nothing is, but because they are far enough away, steady enough, and identifiable enough that everyone's measurements of them converge on the same numbers. Position in deep space is not a fact you discover. It is a consensus you reconstruct from whatever the universe has left lying around that is reliable enough to build a consensus on. The rest of tonight is about what qualifies. The list is very short. It has, in practice, 2 entries, and they are radically different objects with radically different failings. It is worth staying with the frame problem one more beat, because it has a practical edge that catches people by surprise. A spacecraft's velocity is not a single number in its computer. It is a set of numbers, each one attached to a different reference, and a navigator has to keep them straight because they answer different questions. There is velocity relative to Earth, which is what a tracking station measures and what matters for pointing an antenna. There is velocity relative to the Sun, which is what matters for orbital mechanics inside the solar system, because the Sun is what the trajectory is curving around. There is velocity relative to the local group of nearby stars, which is what matters if the destination is one of them. And there is velocity relative to the interstellar medium itself, the gas the ship is actually plowing through, which is what matters for shielding, for erosion, and for anything involving a physical interaction with the space ahead. Those 4 numbers can differ by tens of kilometers per second, and a mistake in which one you are using is not a rounding error. It is a different trajectory. The one that would matter most to a genuinely lost traveler is the 3rd, and it is the hardest to obtain. Knowing your motion relative to the stars in your vicinity requires measuring those stars' motions, which requires identifying them and knowing what their motions are supposed to be, which requires the catalog you may not be able to use. The measurement folds back into the problem it was supposed to solve. There is one measurement that does not fold back, and it deserves a mention because it is genuinely useful and almost nobody thinks of it. Fill the sky with the faint microwave glow left over from the early universe. It comes from every direction, and it is very nearly uniform, but not exactly. Because we are moving through it, it appears very slightly warmer in the direction we are heading, and very slightly cooler behind, by about 1 part in 1,000. That asymmetry is a real measurable velocity indicator, and it works anywhere in the observable universe without needing to identify a single star. It gives you a speed and a direction relative to the early universe. What it does not give you is a position, because that glow looks the same from everywhere. A traveler measuring it learns which way they are going. They learn nothing whatsoever about where they are. That distinction between knowing your motion and knowing your place turns out to be the pattern of this whole subject. Space is generous with velocities and miserly with positions. There is a further complication for a fast traveler, and it turns the sky itself into a moving target. At ordinary speeds, the direction to a star is the direction to a star. At a large fraction of the speed of light, it is not. The apparent positions of objects shift toward the direction of the travel, an effect called aberration, and it is not an illusion of the instruments. It is what the light actually does. The everyday version is rain on a car windscreen. Stand still in vertical rain and it falls straight down. Drive forward and it appears to come at you from ahead, at an angle that steepens with speed. Light behaves the same way, and at relativistic speeds, the effect becomes dramatic. A ship traveling at a substantial fraction of light speed sees the entire sky crowd forward. Stars that were off to the side migrate toward the bow. Stars that were genuinely behind the ship can appear ahead of it. the forward view becomes a compressed, brightened, blue-shifted disk containing most of the visible universe, while the region Austern empties out into a dim red hole. For navigation, this is a serious problem layered on top of every other problem. The pattern matching that a star tracker performs assumes the sky looks the way the catalog says. At relativistic speed, it does not, and the distortion depends on the ship's speed, which is one of the quantities you are trying to determine. The correction is perfectly computable. The mathematics of aberration is textbook material, and a ship that knows its velocity can undo the distortion exactly. But knowing the velocity requires the fix, and getting the fix requires the correction, and the two requirements point at each other. In practice, this is solvable because the ship has a good running estimate of its own speed from its dead reckoning system, and the correction is not sensitive enough to fail on a small error. It is not a wall. It is one more place where the traveler's own state has to be assumed before the measurement can be interpreted, and every such place is a place where a mistake can hide and grow. And there's a quieter version that affects even a slow ship. The Earth's own motion produces an aberration of about 20 arcseconds, which astronomers correct for as a matter of routine. A ship moving at a different velocity has a different aberration, and any catalog it carries was compiled with Earth's correction baked in. The sky is not a fixed backdrop against which motion happens. It is an image that motion changes. Set aside the traveler's motion entirely. Even for an observer who never moves, the sky is temporary, and the time scale is short enough to matter for any interstellar voyage. Stars move, all of them. The sun moves at about 230 kilometers per second around the galactic center, and every star in the neighborhood is doing something similar but not identical. Different speeds, different inclinations, different phases of their own long orbits. The result is that the stars around us are in constant relative drift, and the patterns they make are not structures but momentary alignments. The apparent rate of that drift across the sky is called proper motion, and for most stars it is tiny. The nearest and fastest movers are the exception. Barnard's star, a dim red dwarf about 6 light-years away, crosses the sky at roughly 10 arcseconds per year, the largest proper motion of any known star. 10 arcseconds a year sounds negligible, and over a human lifetime it is about a quarter of the width of the full moon. Over 1,000 years, it is nearly 3 degrees, 6 full moons laid side by side. Over 100,000 years, if it continued in a straight line, it would cross the entire sky several times over. Most stars move far more slowly than that in apparent terms, mainly because they are further away. But the aggregate effect is the same. Run the sky forward 100,000 years, and the familiar patterns do not survive. The most recognizable shape in the northern sky, the 7 bright stars most people can find, comes apart because 5 of its stars belong to a loose-moving group traveling together, while the 2 at the ends do not. The shape stretches, then shears, then stops being a shape at all. And here's what nobody tends to say about the constellations. They are weather. They are not the furniture of the sky. They are a pattern the sky happens to be making during the few tens of thousands of years in which our species has been looking up, and the whole of recorded human history has taken place inside a single frame of a very long film. For a traveler, this compounds every earlier problem. A voyage measured in tens of thousands of years does not merely take you somewhere else. It takes you to a different sky, one that has genuinely rearranged, in which the catalog you carry describes an arrangement that no longer exists. The catalog includes proper motions and can be propagated forward. That is standard practice, but the propagation is only as good as the measured motions, and the errors in those motions grow with every year you extrapolate. The map does not just fail to cover the territory. Given enough time, it stops describing the territory it did cover. There is a thread running through everything so far, and it is time to name it, because it points directly at the solution. Every method that actually worked by measuring time. Satellite navigation is a time measurement. The satellites broadcast timestamps. The receiver compares arrival times, and the differences become distances only because light travels at a known speed. Deep space network ranging is a time measurement, a round trip clocked and halved. Delta differential one-way ranging is a time measurement, the difference in arrival at two antennas. Doppler tracking is a time measurement wearing the costume of a frequency, since frequency is just how often a wave arrives. The methods that failed because they were trying to use something other than time. Looking out of the window is an attempt to use angles and apparent brightness, and both are corrupted by the unknown distance. Dead reckoning is an attempt to use inertia, and it drifts. Parallax is an attempt to use geometry, and geometry runs out of baseline. Time does not have those weaknesses. A clock does not care how far away you are. It does not care what direction you are facing, whether there is dust in the way, or whether anyone at home is still transmitting. If you have a signal that carries a reliable timestamp, and you know when that stamp was supposed to have been sent, then the delay tells you the distance, and no other information is required. That is the whole principle, and it explains exactly what a deep space traveler needs. Not a landmark. A clock. Several clocks in different directions, all of which the traveler can read, and all of which behave in a way that was known before departure. The requirements are severe. Each clock must be visible from anywhere in a large volume of the galaxy, which means it must be extremely bright or emit in a band that passes through dust. Its rate must be known and must stay known for the length of a voyage, which means it must be stable over thousands of years, not decades. It must be individually identifiable, so you can tell which clock you are reading. And nobody can be maintaining it, because nobody will be. Written like that, it sounds like a specification for something that does not exist. A natural object that keeps time to a precision comparable with a laboratory standard, shines across a galaxy, survives for millions of years, and comes with a distinguishing signature. Such objects exist. There are thousands of them. They have been known since 1967, and the entire discipline of deep space navigation without Earth rests on them. A pulsar begins with a dying star. When a star considerably more massive than the Sun exhausts its fuel, the outward pressure that held it up disappears in seconds, and the core collapses. Electrons and protons are crushed together into neutrons, and the collapse halts only when the neutrons themselves resist being packed more tightly. What remains is an object with more mass than the Sun compressed into a sphere roughly 20 kilometers across, a city-sized ball with the density of an atomic nucleus, where a sugar cube volume would weigh about as much as a mountain range. Two things about the collapse matter for navigation, and both are consequences of ordinary conservation laws. The first is rotation. Every star spins slowly. Shrink a spinning object and it must spin faster, for the same reason a skater speeds up when pulling their arms in. Take a star rotating once a month and compress it from 1,000,000 kilometers across to 20, and the rotation rate increases enormously. Young neutron stars rotate several times a second. The second is magnetism. Stars have magnetic fields, and squeezing a magnetic field into a far smaller volume concentrates it ferociously. A neutron star's magnetic field can be 1,000,000,000,000 times stronger than Earth's. Now put those together. The magnetic axis is generally not aligned with the rotation axis, the same way Earth's magnetic pole does not sit at its geographic pole, and charged particles accelerated along the magnetic axis pour out radiation in two narrow beams from the magnetic poles. The star rotates. The beams sweep around like the lamp in a lighthouse. If one of those beams happens to sweep across the solar system, we detect a pulse each time it passes. Not a star that blinks, a beam that rotates, catching us once per turn. This is why the phenomenon looks so improbable when first encountered, and why the earliest detection in 1967 was cataloged half-jokingly as a candidate signal from someone else before the astrophysics was worked out. A signal arriving with the regularity of a metronome from a fixed point in the sky is not what anyone expected the universe to produce on its own. But there is nothing exotic in the mechanism. A heavy flywheel spinning in a vacuum with a lamp bolted to it at an angle. The flywheel has the mass of a star and essentially nothing to slow it down. That is the entire device, and it is the steadiest device the universe makes. It is worth noticing how much of that steadiness is an accident of housekeeping. Every clock humans build has to be protected from temperature, from vibration, from pressure, from magnetic fields, from the slow chemical decay of its own components. A cesium standard sits in a laboratory with the environment held constant around it by people whose job is to hold it constant. A pulsar has none of that and needs none of it. Its stability does not come from care. It comes from inertia, which is the one form of protection that requires no protector. That distinction is the reason this class of object matters for a traveler, and no laboratory instrument ever could. A clock that needs looking after is a clock that fails when the looking after stops. A collapsed star turning in a vacuum has no maintenance schedule to interrupt, and there is nothing anyone could do to it, or fail to do for it, that would change its rate. Ordinary pulsars are good clocks. A specific subclass of them is extraordinary, and the difference comes from a second act in their lives. A young pulsar spins a few times a second and slows measurably as it radiates away rotational energy. Over millions of years, it winds down, and eventually the beam shuts off. That would be the end of it, except that many stars come in pairs. If a neutron star has a companion, and the companion swells in old age, material can spill from the companion onto the neutron star. That falling material does not arrive straight down. It spirals in, carrying angular momentum, and it spins the neutron star up. The process is called recycling, and it takes an old, slow, nearly dead pulsar and drives it to rotate hundreds of times per second. These are millisecond pulsars, and their rotation periods are measured in thousandths of a second. The one worth naming is PSR J0400 and 37 to 4715, the closest and brightest millisecond pulsar known. It rotates 173.7 times every second. Its period is about 5.757 milliseconds. Hold that image for a moment. An object more massive than the Sun, 20 kilometers across, turning on its axis 173 times in the time it takes to say the word, and doing so with a steadiness that measures roughly 1 part in 10 to the 15th, a fractional stability comparable to a good laboratory frequency standard. The reason for the steadiness is mass. A spinning flywheel resists changes to its rotation in proportion to its moment of inertia, and this flywheel has the mass of a star packed into a city. There is essentially nothing in the universe that can nudge it. It sits in a vacuum. It has no moving parts. It requires no power, and it will keep turning for hundreds of millions of years. Here's where honesty is required, because this is a subject where the claim regularly outruns the evidence. On short timescales, the best atomic clocks humans have built are clearly steadier than any pulsar. A cesium or optical lattice standard in a laboratory beats a neutron star over days and months without any argument. It is only when you go out to timescales of about 10 years and longer that the best millisecond pulsars become genuinely comparable, because atomic clocks drift slowly over long periods while a flywheel with the mass of a star does not. Pulsars are also not perfectly behaved. They exhibit timing noise, low-level wandering in their arrival times. Some, especially younger ones, glitch, abruptly speeding up, apparently from a readjustment inside the star. The millisecond ones are far better behaved than the young ones, which is exactly why they are the ones anybody proposes to navigate by. So the correct statement is careful. Millisecond pulsars are the most stable natural clocks known, comparable to atomic standards over decade-long baselines, and free of the one thing every human clock requires: somebody to keep it running. Understanding how a pulsar becomes a position starts with a single conversion, and it is the same conversion that underlies all satellite navigation. Light travels roughly 300 million meters in 1 second. In 1 millisecond, it travels 300 kilometers. In 1 microsecond, it travels 300 meters. So if you can measure the arrival time of a pulse to 1 microsecond, you have measured a distance to 300 meters. That is the exchange rate between timing precision and range precision, and it is fixed by the speed of light and nothing else. Now consider what a pulsar gives you. It sends a pulse toward you at absolutely regular intervals. For J04374715, one every 5.757 milliseconds. You know the interval in advance because it was measured from Earth for years before you left, and its slow, steady spin down was measured too. so you can predict the interval at any future date. You observe the pulses. You compare when they actually arrive against when your model says they should have arrived. The difference is called the timing residual, and it contains your position, specifically the component of your position along the line to that pulsar. If you are farther from the pulsar than your model assumed, the pulses arrive late by exactly the light travel time of the excess distance. One pulsar gives you one number, your displacement along one line. It cannot tell you anything about your position perpendicular to that line because moving sideways does not change the distance to a very distant object. Take a second pulsar in a different direction and you get a second line. Take a third and the three constraints intersect at a point. That is a three-dimensional fix, built entirely from timing, using objects that nobody maintains and that will still be there in 1,000,000 years. There is one wrinkle, and it is the same wrinkle that appears in every phase-based measurement. The pulses are identical. If you catch one, you know where you are within one pulse period, but you do not know which pulse it was. For J04374715, one full period corresponds to light traveling about 1,726 kilometers. So a single measurement locates you along that line to within 300 meters, modulo a ruler that repeats every 1,726 kilometers. Resolving that ambiguity is what the extra pulsars and the ship's dead reckoning estimate are for. The rough position from inertial navigation tells you which cycle you are in. The pulse timing tells you exactly where within it. The two systems cover each other's weaknesses precisely. One is accurate but ambiguous. The other is unambiguous but drifting. That combination is not a thought experiment. It has been built, flown, and demonstrated. The principle is clean. Building an instrument that can execute it is not. And the difficulty is worth understanding because it explains why this took until the 21st century. The problem is photon starvation. A pulsar's X-ray output is enormous at the source and negligible by the time it reaches us, because it has spread across a sphere hundreds or thousands of light years in radius. From a good millisecond pulsar, a detector might collect a handful of X-ray photons per second. Not thousands, a handful. Now consider what has to be measured. The pulse profile, the shape of the brightness rising and falling as the beam sweeps past, has to be reconstructed accurately enough to time its arrival to a microsecond. With a few photons per second and a period of 5.757 milliseconds, no single rotation produces a recognizable pulse at all. Most rotations produce nothing. The profile has to be built by folding, recording the arrival time of every photon, then stacking them all according to where they fall within the predicted cycle, so that thousands of rotations worth of scattered photons accumulate into one smooth curve. That folding is only possible if you already have a good prediction of the period, which is why the timing model matters so much. Fold with a slightly wrong period, and the pulses smear into a flat line instead of adding up. The signal is not lost because it was too faint. It is lost because it was stacked out of phase. So the instrument requirements are severe in two directions at once. It needs a large collecting area to gather photons faster. And it needs exceptionally precise time tagging on every individual photon, since the timing of each one is the actual measurement. This is what NICER was built for. It is not one telescope. It is 56 X-ray concentrators, each with its own silicon detector, all pointed together, and the whole assembly time tags arrivals to well under a microsecond against an onboard clock disciplined by satellite time. The astrophysics case for that design and the navigation case turn out to be the same case. Both want as many precisely timed photons as possible from a very faint, very fast source. And this is the constraint that shapes everything about how such a system would work in practice. A pulsar fix is not instantaneous. It is an integration. You point at a source and collect for minutes or hours until enough photons have accumulated to place the pulse arrival with confidence. Then you swing to the next source and do it again. A ship navigating this way is not reading a display. It is running a patient observing campaign against 4 or 5 targets in sequence, assembling a position over the better part of a day, while its inertial system carries the estimate forward in between. That is not a limitation of the demonstration. That is what the method is, and it is why it pairs so naturally with dead reckoning rather than replacing it. In November 2017, NASA ran the experiment. The instrument was NICER, a box of 56 X-ray telescopes mounted on the outside of the International Space Station. Its primary job is astrophysics, studying neutron stars, measuring their sizes, working out what matter does at densities nothing on Earth can reproduce. But NICER was built with a second experiment riding along inside it, called SEXTANT, and SEXTANT had a different purpose entirely. It was there to find out whether a spacecraft could work out its own position from pulsars in real time with no help from the ground at all. Over the Veterans Day weekend, across roughly 2 days, the SEXTANT software took control. It selected 4 millisecond pulsars, cataloged as J0218 plus 4232, B182124, J0030 plus 451, and J04374715, and directed NICER to swing from one to the next, gathering X-ray photons from each in turn. It knew the expected pulse arrival times. It measured the actual ones. It fed the residuals into an onboard filter and produced, without any input from Earth, an estimate of where the station was. The results were better than the goal. The experiment's formal performance target was to reach a position accurate to within 10 kilometers in the worst direction. The onboard solution converged below 10 kilometers within about 8 hours and stayed there for the rest of the run, with the filter's own uncertainty estimate holding under 30 kilometers. During good stretches, the position was accurate to about 3 miles, roughly 5 kilometers. Read that back slowly, because it is a genuinely remarkable sentence. A spacecraft determined its own location to within a few kilometers, autonomously, in real time, using nothing but the light of 4 dead stars, each of which had been emitting that light for millions of years before anyone existed to think of using it. The stars did not know. The stars were not built for this. 4 collapsed cores, thousands of light years apart, spinning for reasons that have nothing to do with us, happen to constitute a usable navigation system, and it took our species until the 21st century to notice we could read them. The lead investigator's summary was direct. The demonstration establishes the viability of X-ray pulsar navigation as an autonomous capability, and a mature version of the technology could support deep space exploration anywhere in the solar system and beyond. Notice the tense in that last sentence. It is doing a great deal of work, and the next segment is about exactly what it means. This is the part where it matters to be careful, because pulsar navigation is a subject that attracts overstatement, and the real result is impressive enough that it does not need any help. Start with where the experiment took place. Sextant ran on the International Space Station in low Earth orbit, about 400 kilometers up. That is as close to home as a spacecraft can be while still being a spacecraft. It is inside the satellite constellation, inside the tracking network, inside every conventional navigation system we have. That location was not a limitation of ambition. It was the point. The station's position was already known, continuously, to far better precision than the pulsar solution could deliver, which meant there was a truth to check the answer against. You cannot validate a navigation system somewhere you do not already know the answer. The demonstration had to happen where the method was least needed, precisely so that its output could be graded. So what was proved is specific: that the timing models were good enough, that the onboard filter worked, that an autonomous system could take raw X-ray photons and converge on a correct position without assistance. Those were the open questions, and they were answered. What was not proved is everything about deep space. Nobody has flown this beyond Earth orbit. Nobody has demonstrated it where the geometry differs, where the pulsar timing models must be extrapolated over far longer baselines, or where there is no independent answer to check against. And nothing currently flying anywhere in the solar system navigates by pulsars as its primary means. Every operating deep space mission is still navigated the conventional way, by radio, by a conversation with Earth, exactly as described earlier tonight. The performance figures deserve the same care. 10 kilometers is a superb result for a first autonomous demonstration. It is also 10 kilometers, not 10 meters, and the frequently quoted deep space ambition of a few hundred feet is a target for a mature version of the technology, not a number anyone has achieved. Between the demonstration and that target lie better detectors, longer integration times, refined timing models, and a great deal of work that has not been done yet. And here is the thing worth saying plainly. It is genuinely rare to find a technology where the honest version is more interesting than the exaggerated one. The exaggerated version is a galactic positioning system. The honest version is a spacecraft in low orbit, quietly working out where it was from 4 rotating stars for the first time in history, over a long weekend. The second one is better because it actually happened. The reach of this method is the whole reason it matters, and it comes from the physics of what a pulsar emits. Consider the anchor number, more time, and set it against the pulsars. Past 55.8 light years, the sun is gone from human sight. Past a few thousand light years, parallax has stopped delivering usable distances. Past the dust lanes, whole regions of the sky have gone dark in visible light. The pulsars used in the Sextant experiment do not care about any of that. They lie at distances of hundreds to thousands of light years, and they are detected not by their visible light, but by X-rays and radio waves. Radio waves pass straight through the dust that blocks the galactic center from view. X-rays are produced by processes so energetic that a pulsar outshines, in that band, objects that would be invisible beside it in ordinary light. And crucially, the signal is not a brightness, it is a rhythm. A star's brightness degrades with distance until it drops below your detection threshold and you lose it. A rhythm degrades differently. As the signal gets fainter, you need to collect for longer to see the pattern. More photons, more integration time, but the pattern itself does not change. The period of J04374715 is 5.757 milliseconds, whether you observe it from here, from 1,000 light years away, or from the far side of the galaxy. Distance costs you observing time. It does not corrupt the measurement. That is the property nothing else on the list has. Brightness lies about distance. Angles lie without distance. Patterns of stars change with viewpoint. A rotation period is the same number everywhere, for everyone, forever, and it is a number nobody has to agree to. There is a real limit, and it is honest to state it. The timing model, the precise prediction of when pulses should arrive, has to remain valid. Pulsars spin down at a slow, measured rate, and that rate can itself change slightly over long periods. A model calibrated today and extrapolated 1,000 years forward will have accumulated error, and one extrapolated 100,000 years forward may have become useless. There is also the interstellar medium itself, which delays radio waves by an amount that depends on the electron density along the path and on the frequency, so a traveler on an unfamiliar route is correcting for a medium they have not measured. But within those bounds, the pulsars are the one thing on the entire inventory that keeps working after everything else has quietly failed. When the sun is invisible, when the chart has run out, when the dust has closed the sky and nobody is answering the radio, there are still several thousand flywheels turning in the dark, each one keeping its own time, each one readable by anyone with a detector and the patience to integrate. Humans understood this before anyone could use it, which is one of the more affecting facts in the history of space exploration. In March 1972, Pioneer 10 launched toward Jupiter and beyond it, out of the solar system entirely. Bolted to its antenna support was a gold anodized aluminum plaque, 6 inches by 9, engraved with a message. The astronomer Frank Drake devised the central element of the design. Carl Sagan and Linda Saltzman-Sagan worked with him on the whole, and the three of them described it in the journal Science that year under the title, A Message from Earth. Most people remember the human figures on the plaque. The navigationally serious part is the other element, a starburst of 14 lines radiating from a single point. The point is the sun. Each line runs toward a pulsar, and the length of each line indicates the relative distance to it. Along each line are tick marks in binary, a series of long and short dashes encoding a number. That number is the pulsar's rotation period, expressed as a multiple of a fundamental time unit defined elsewhere on the plaque by the hydrogen atom, a physical constant available to anyone, anywhere in the universe. The design is a position statement with no language in it at all. A finder who recovers the plaque identifies several of those pulsars by matching their periods to what they observe and works backward from the encoded distances, can locate the sun in 3 dimensions. And because the encoded periods were measured in 1972, and because pulsars slow at known rates, a finder can also determine roughly when the plaque was made by seeing how far each pulsar has drifted from its stated period. It is a map and a date stamp in one object, written in the only alphabet the universe distributes for free. The same starburst was engraved on the cover of the Voyager Golden Record 5 years later, and both Voyagers carry it now, well past the edge of the solar system. Sit with the strangeness of it. In 1972, nobody could navigate by pulsars. The technology to do it autonomously would not be demonstrated for another 45 years, and would then be demonstrated in low Earth orbit rather than deep space. But the principle was understood well enough that a team designing a message for an unknown recipient at an unknown time chose pulsars as the one reference that would still make sense. They were designing for a reader who would have none of the things we rely on. No shared language, no shared units, no shared history, no access to any of our catalogs. And the answer they arrived at was, use the clocks. Everyone gets the same clocks. 3 pulsars are enough to fix a position in 3 dimensions. Drake used 14, and the reasoning behind that surplus is the most quietly humble thing about the design. The first reason is that pulsar beams are directional. A pulsar is only a pulsar if its beam sweeps across you. A neutron star whose beam happens to miss your line of sight is not a faint pulsar. It is not a pulsar at all from where you stand. Every pulsar we know about is one whose geometry happens to favor us, and a finder somewhere else in the galaxy would have a different set. Some of the 14 would simply not exist for them. The second reason is that pulsars fade. They spin down. Their beams weaken, and after some tens of millions of years, the emission mechanism shuts off. A plaque intended to survive an unbounded amount of time, and Pioneer 10 will drift for far longer than the sun will shine, cannot assume that any particular source will still be broadcasting when it is found. The third reason is obstruction. The finder might be behind dust, or in an unfavorable part of the galaxy, or looking at some of those sources through a region that scatters their signal beyond recognition. So the redundancy is not decoration. It is an admission written into the geometry that the designers did not know who would find it, when or from where, and that a design robust to those unknowns needs far more references than the arithmetic strictly requires. There is a fourth reason worth noting, and it is purely practical. Identifying a pulsar from its period alone is not certain. Periods are distinctive but not unique. Among the thousands of known pulsars, some have similar rotation rates. 14 simultaneous constraints, each with an encoded period and a relative distance, cross-check each other so thoroughly that a wrong identification collapses immediately. 3 would be a puzzle with a solution. 14 is a puzzle that proves its own answer. That is an unusual thing to find in a message. Most messages assume a recipient who shares context. This one assumes nothing at all and compensates by being overdetermined, by saying the same thing so many different ways that no single failure can break it. It is worth asking, at least once, whether we do anything else with that much care. The plaque was designed for a reader who might not exist, might not be human, might not arrive for a billion years and would arrive with no shared anything. The design response was to be more redundant than necessary and more honest than required about what could go wrong. The plaque is not permanent, though, and understanding why closes the loop on the pulsar method's real limits. Pulsars slow down. The rotational energy driving the beams has to come from somewhere, and it comes from the spin. A young pulsar loses rotation rate quickly enough that the change is easy to measure over a few years. Millisecond pulsars, being older and having been spun back up by accretion, slow far more gently. But they do slow, and over long enough spans the drift is substantial. That gives the plaque its date stamp, which was intentional. It also gives it an expiry, which was unavoidable. The encoded periods were correct in 1972. A finder recovering the plaque in 10,000 years will observe periods that have drifted from the engraved values and can use the difference to compute the elapsed time. A finder recovering it in 10 million years may find that several of the sources have stopped pulsing entirely, that others have drifted so far that identification is ambiguous, and that the remaining few no longer overdetermine the solution. The same erosion affects a traveler's onboard timing model, and it is the practical ceiling on how long pulsar navigation stays accurate without recalibration. The model is a set of coefficients describing each pulsar's period and how that period changes. Both were measured over some finite span of observation from Earth. Extrapolating them forward is like extrapolating any fitted curve, fine for a while, then increasingly speculative, with the error growing faster than the extrapolation. For a voyage of decades, this is a non-issue. The models are good for that. For a voyage of millennia, it becomes a real source of error. And for a voyage of the kind that would actually take you beyond the region already mapped, the timing models a ship departed with would need to be maintained by the ship itself, continuously remeasuring its own reference clocks against a standard it carries, while moving relative to them at a velocity it is trying to determine. There is a genuine circularity there, and it does not fully resolve. It can be managed. A ship with a good internal frequency standard and a long observing baseline can rebuild its own pulsar ephemeris as it travels. But the rebuild depends on the ship's own clock, and the ship's own clock is exactly the kind of maintained human artifact the pulsars were supposed to replace. The universe supplies clocks that need no maintenance. It does not supply a way to read them that needs no maintenance. That gap is small, and it is real, and it is where the elegance of the whole scheme finally admits an engineering cost. There is one other class of object on the inventory, and it is the strangest entry on the list, because it is simultaneously the most reliable and the most useless. The modern celestial reference frame, the coordinate system that all precise astronomy is quoted in, is not defined by stars. Stars move. It is defined by quasars. A quasar is the luminous core of a distant galaxy, powered by matter falling onto a supermassive black hole, radiating more energy than all the stars in its host galaxy combined. They are among the brightest sustained objects in the universe, and they are extraordinarily far away, billions of light years typically. That distance is the point. Everything moves, but apparent motion across the sky falls off with distance. A quasar billions of light years away can be traveling at an enormous physical speed and still show essentially no measurable drift across our sky over decades of observation. For practical purposes, they are nailed in place, and they are the only things that are. The current realization of this frame is called ICRF-3, adopted by the International Astronomical Union in 2018. It contains 4,536 radio sources. Of those, 303 are defining sources, chosen for their stability and their sky distribution, and they are what actually pins the orientation of the frame. The noise floor is around 30 microarcseconds, with median position uncertainties of roughly 1/10 of a milliarcsecond in one coordinate and 2/10 in the other. That is the most precisely determined set of directions in existence. Every spacecraft trajectory, every telescope pointing, every published stellar position is ultimately referred back to those objects. And the delta differential ranging technique described earlier works by comparing spacecraft signals directly against them. Now the irony. Quasars give you orientation and nothing else. They are so far away that their directions are identical from anywhere in our galaxy. Travel 10,000 light years, and the quasars have not shifted in any measurable way, which is exactly what makes them useful as a fixed frame and exactly what makes them worthless as a position reference. A traveler who observes the quasars learns which way is which to breathtaking precision and learns absolutely nothing about where they are. So the two entries on the inventory divide the problem cleanly, and neither can do the other's job. The quasars are perfectly fixed and give you no position. The pulsars give you position and are slowly running down. Between them, a traveler far from home can determine their orientation to microarcseconds and their location to some kilometers, using objects nobody built and nobody maintains. That is a real answer to the question this episode asked. It is worth admiring for a moment, because in a subject full of walls, it is the one door. And it is also in the way that matters most. Not enough. Everything so far has answered a question that turns out not to be the one in the title. The instruments answer one question, which is where the ship is. The title asks a different one, which is how the ship gets home. Those sound like the same problem separated by one step of arithmetic. They are not. They are different problems with different physics, and only the first one has a solution. Suppose the pulsar system works perfectly. The ship integrates for a few hours, resolves its cycle ambiguities, and produces a position good to a kilometer. It knows where it is. It also knows where the sun is because the sun's position in the galactic frame was recorded before departure. Subtract one from the other and you have a vector, a direction and a distance, exact, unambiguous, sitting on a display. What has changed? The ship's velocity has not changed. Its fuel has not changed. Its structural limits, its life support margins, and the ages of everyone aboard have not changed. A vector on a screen is information, and information does not move mass. The problem of returning was never a problem of not knowing which way to point. It was always a problem of energy, and energy is indifferent to how well informed you are. This is the thing that gets lost in every version of this story, and here's the plainest way to put it. Being locatable and being recoverable are two entirely different conditions, and space grants the first one freely while withholding the second absolutely. Consider the ordinary human experience the phrase draws on. When a person is lost on a mountain, finding out where they are is genuinely the hard part, because once located, a helicopter covers the distance in 20 minutes. The whole emotional weight of the word rescue rests on that asymmetry, that locating is difficult and retrieving is easy. Every rescue story a person has ever heard is built on it. In deep space, the asymmetry inverts completely. Locating is the tractable half. There are 4,500 quasars holding the frame steady and several thousand pulsars keeping time. And between them, a sufficiently patient ship can always work out where it is. Retrieving is the impossible half, and it is impossible not because of any missing knowledge, but because of the numbers involved in changing a velocity across an interstellar distance. So the honest reading of the title is not that a traveler could never determine their position. They could. The universe supplies the means, and we have demonstrated that we can read them. The honest reading is that determining it changes nothing. You would know precisely where you were, precisely how far from home, and precisely which direction to face. And you would be exactly as far away as you were before you knew. The arithmetic of coming back is worth doing plainly, because it is where the last hope quietly goes. A ship traveling away from home at some speed has to do three things to return. It has to cancel the velocity it has. It has to acquire an equal velocity in the opposite direction. And then, on arrival, it has to cancel that one too, unless the plan is to pass through the solar system at interstellar speed and keep going. Each of those is the same size of task as the original departure burn. Coming back is not a modest correction. It is 3 more departures, and every one of them has to be paid for out of propellant the ship is already carrying, since there is nowhere to refuel. The rocket equation makes this brutal in a way that is not intuitive. The propellant required does not scale with the velocity change. It scales exponentially with it. Doubling the velocity change does not double the fuel. It squares the mass ratio. A mission that needs a mass ratio of 10 to reach a certain speed needs a mass ratio of 100 to reach it and stop, and 10,000 to reach it, stop, come back, and stop again. That is why every deep space mission humans have flown is one way. Not because we lacked ambition, but because the return trip is not an increment on the outbound trip. It is a different mission, several times over, and the propellant it demands does not exist in any configuration anyone has designed. There is one trick the solar system offers, and deep space does not. Inside a planetary system, a spacecraft can steal momentum from a planet, swing past it on a carefully chosen path, and leave with a different velocity, having borrowed from the planet's orbital motion. It is how the Voyagers reached the outer planets and left the system entirely on a fuel budget that could never have done it directly. Between the stars, there is nothing to swing past. The gravity assist is a technique for navigating a crowded neighborhood, and interstellar space is the definition of an uncrowded one. Whatever velocity a ship has out there, it keeps, unless it spends propellant to change it. Space is frictionless, which is generous going out and merciless coming back. So the vector on the display, the one produced by all that careful pulsar timing, points along a route that cannot be flown. The direction is correct. The distance is correct. The trip is arithmetic that does not close. There is a last version of hope worth taking seriously, because it is the one people reach for instinctively. If the ship cannot come home, perhaps home can come to the ship. Work through what that would require. First, home has to know something is wrong. At 4 light years, the news takes over 4 years to arrive. At 55.8, it takes 55.8. There is no faster channel. The signal moves at the speed of light, and nothing carries information faster. So the request for help is not late in the way a delayed phone call is late. It is a historical document by the time it arrives, describing a situation whose participants have long since resolved it, one way or another. Second, home has to be in a position to act. That means a launch-ready vessel capable of interstellar flight, crewed or automated, sitting available on the day the message lands. Not designed, not proposed. Built, fueled, and waiting. Third, that vessel has to make the crossing. And here the arithmetic from the previous segment applies to the rescuer as well. It has to accelerate, cross, decelerate to match the stranded ship's velocity, and then, if the point is to bring anyone back, accelerate again, cross again, and decelerate again. The rescue mission is 4 velocity changes where the original voyage needed 1. Add up the timeline. The message crosses. The mission is prepared. The mission crosses slower than light, then the return crossing. Even under absurdly generous assumptions, the total elapsed time is several times the one-way light travel time, which was already measured in years or decades or centuries, depending on the distance. Nobody aboard the stranded ship is alive at the end of that arithmetic. Very likely nobody who launched the rescue is either. The concept of rescue has an implicit clause that never has to be stated on Earth, that the rescuers and the rescued will be alive at the same time. And interstellar distance is precisely the regime where that clause fails. This is what it means to say that being found is not the same as being reachable. A ship far enough out could be located to the kilometer by anyone who cared to look. Its position could be published, cataloged, known, and that perfect knowledge would sit in an archive somewhere, entirely accurate, entirely useless, a set of coordinates for a place nobody can go. The universe is willing to tell you where things are. It has no mechanism for bringing them back. There is one more subtraction, and it is the only one that has nothing to do with physics. Suppose everything worked. Suppose the pulsar fix was perfect, the propellant somehow sufficient, the trajectory closed, and a ship that left for the deep actually turned around and came back. What would it be returning to? The answer depends entirely on how long it took, and interstellar voyages are long. A round trip to even a nearby star at any speed we can presently imagine achieving runs to many decades at minimum. To anywhere genuinely distant, it runs to millennia. Over a few decades, home is recognizably home, changed in the way any place changes across a lifetime. Over a few centuries, the language has shifted. The institutions that dispatch the mission are gone, and the records of it are historical rather than operational. Over tens of thousands of years, the returning ship arrives at a planet whose relationship to the departure is essentially archaeological, assuming the destination is still a functioning place at all, which is an assumption with no evidence behind it in either direction. And the sky the ship departed under will not be the sky it returns to. That is the proper motion problem from earlier applied to the traveler's own memory. The constellations they left will have shifted. The stars they used as references will have moved. The map they carried out will not describe the sky they come back to, and the difference will be large enough to notice. So the word home carries a hidden assumption, and it is the same assumption that made rescue fail. Home is not a set of coordinates. It is a set of coordinates plus a time plus a set of people. And the coordinates are the only one of the three that a navigation system can deliver. This is why the title question has the answer it has. Not because the position is unfindable. It is findable by the methods described tonight using objects the universe supplies for free. But because a position was never what anyone meant by home, and the parts they did mean are exactly the parts that no instrument measures and no amount of precision recovers. You could stand on that ship with a perfect fix on the display, knowing your location to within a kilometer, knowing the exact bearing to the star you were born under, and still be as far from home as it is possible for a person to be. The number would be correct. The number was never the thing. There is one thing that makes the return crossing, and it is worth ending the argument on it rather than on the losses. Information comes back. Not fast and not usefully for anyone aboard, but reliably and forever. A signal transmitted from a ship in deep space travels outward at the speed of light and does not stop. It weakens, spreading over an ever larger sphere, its power falling with the square of the distance. But it does not decay, and it does not turn around, and it does not need anybody to carry it. If someone is listening with a large enough collecting area and enough patience, the message arrives. This is the asymmetry that makes deep space survivable as an idea, even though it is not survivable as a journey. Mass cannot make the round trip. Information can make the one-way trip indefinitely. A ship that will never come back can still be heard, and everything it learned can arrive at the place that sent it, long after the sending and long after the involved evolved. That is precisely what the Pioneer plaque is, read correctly. It is not a navigation instrument, and it never was. It is a one-way message on a vehicle that will never return, carrying a position fix for a star system that the reader could locate but could not reach, engraved by people who understood both halves of that perfectly well and sent it anyway. And it is what the Voyagers are doing at this moment, at the far edge of what we can still hear. Voyager 1 sits roughly 170 astronomical units out, its signal taking about 23 hours to reach us, and on the 18th of November, it will stand one full light day away, the first thing our species has built to reach that mark. It will never come back. Everything it has ever told us did. So the honest ledger of deep space reads like this. It takes the ground, the horizon, the scale, the landmarks, the network, and the conversation. It takes the sun itself at 55.8 light years. It leaves the pulsars and the quasars, which are enough to answer where. It refuses, absolutely, to answer how do I get back. And it permits, at no cost and without limit, the one-way transmission of everything you found out. That is not nothing. That is, in fact, the entire arrangement under which every discovery in the history of exploration has eventually been useful, compressed to its bare form and stripped of the part where anyone comes home. We have talked about a ship in perfect condition, with every gauge inside its band, unable to name a direction. We have talked about how a position is not a property, but a relationship, and how deep space is the systematic removal of the things a relationship needs. We have talked about the 5 gifts the planet gives a navigator: a flattened problem, a stationary reference, a level horizon, a known scale, and a broadcast network, and how each one is a local convenience rather than a property of the universe. We have talked about dead reckoning and the bias that integrates twice, and the 4,900 kilometers of error a very good instrument accumulates in a single quiet year. We have talked about the satellite constellation that broadcasts downward and stops, and the deep space network that answers when it can, and the 1-nanoradian angle that becomes 25 kilometers at Voyager's distance and 500,000 at 55 light years. We have talked about the 2-day-old map and the 8.5-year correspondence with the nearest star, and the moment when a conversation becomes an archive. We have talked about parallax, the one honest measurement, standing on a baseline of 2 astronomical units that no amount of effort will widen enough to matter. We have talked about 1.8 billion cataloged stars, which is about 1% of a galaxy, with the center of it hidden behind 30 magnitudes of dust, a trillion-fold dimming that kept the heart of the Milky Way invisible to every human being who ever lived until the last 100 years. We have talked about a universe with no still point, where every velocity is a velocity relative to something you chose. We have talked about a sky that shifts when you move and ages when you wait, and constellations that are weather rather than furniture. We have talked about collapsed stars turning 173 times a second, steady to 1 part in 1,000 million million, and about 4 of them in November 2017, telling a spacecraft where it was to within a few kilometers, with nobody on Earth helping. We have talked about 4,536 quasars holding the sky steady to 30 microarcseconds, perfectly fixed and perfectly useless for telling you where you stand. We have talked about photon starvation and folding thousands of rotations together to build one pulse out of a handful of arrivals per second, and why a fix out there is an observing campaign rather than a reading. We have talked about 14 lines radiating from a small yellow star, engraved in 1972 for a reader who might not exist, overdetermined on purpose by people who knew exactly how much they did not know. We have talked about the rocket equation, and about a return trip that is 3 more departures, and about the fact that between the stars, there is nothing at all to swing past. We have talked about rescue as a word with a hidden clause, that the rescuers and the rescued should be alive at the same time, and about the distances at which that clause quietly stops holding. And we have talked about the difference between a fix and a route. So, why could you never find your way home in deep space? The answer arrives in layers, and the first layer is the one everyone expects, and it is wrong. It is not that your position is unknowable. Your position is knowable. The universe has left several thousand clocks running in the dark, each one turning with a steadiness no maintenance schedule could improve on, each one readable by anyone with a detector and time to spend. A ship far from everything can determine where it is. We have proved a version of that in orbit over a long weekend in November, using 4 dead stars and a box of X-ray telescopes. The second layer is that a position is an answer to the wrong question. Knowing where you are does not move you. The vector on the display is correct, and the trip it describes cannot be flown because coming back is 3 more departures, and the propellant scales exponentially, and there is nothing between the stars to borrow momentum from. The direction was never the difficulty. The difficulty was always the energy, and information does not carry mass. And the third layer is the one that has been underneath the whole episode. Home is not a coordinate. It is a coordinate and a time and a set of people, and a navigation system delivers exactly one of those 3. You could hold a perfect fix and be precisely as lost as before, because the thing you were looking for was never in the class of things that instruments find. There is something in that worth carrying back down to the ordinary world, where nobody is stranded and the stars are just decoration. Every place you have ever thought of as home was a relationship, not a location. It was the arrangement of people around you and the particular year and the fact that you could get back. The address was the least of it. People move house and stay home. People sit in the room they grew up in and are not home at all. The coordinates were always doing less work than they appeared to be. And the sky above that room contains a fact worth keeping. Our sun has an absolute magnitude of about 4.83, and the human eye reaches magnitude 6, and those 2 numbers together produce a distance, 55.8 light years. That is the range of home. Travel further in any direction, and the star that made every atom in your body drops below the threshold of human vision and does not come back. 13 times the distance to the nearest star, 2,000 suns in that sphere, 100 billion outside it. Not a wall, a threshold, crossed in an ordinary week without ceremony by anyone who kept going. The instruments would all keep working. The gauges would stay inside their bands. The pulsars would keep their time, 173 turns a second, patient and indifferent and free. And somewhere behind, in a direction the arithmetic could name and the eye could not find, a small yellow star would go on shining for everyone who stayed. Good night.